Hello everybody, MoNaCo here, our fourth homework video for our fourth unit. We're talking about naming and writing chemical formulas. That's what we're starting to do here. But today, you're going to understand how to assign oxidation numbers to atoms, ions, and polyatomic ions that are part of a chemical compound so the compound does not have an ionic charge. You're basically going to start to use the oxidation numbers from the periodic table to explain how atoms combine into compounds. You're also going to start to get familiar with polyatomic ions off of our reference materials, reference table E, and understand a little bit more about what those are and how they play the game. So our lead-in here is a little bit different than usual. How do we figure out a formula for a stable molecule so we can name it? There's a couple rules that we have to follow in order to build stable molecules. The first is assigning oxidation numbers to the elements so that we can get the oxidation states, the numbers to all balance out. Then we work back to balance the oxidation numbers, and so the compounds we form are neutral, so not ions. Compounds that we like to form are neutral. An example here is H2SO4. Well, hydrogen has an oxidation state of +1. There's two of them, so that's why you have a +2 down here. Sulfur has an oxidation state of +6, and there's only one of them, so that's why we have the +6 down here. And oxygen has a -2 times 4, which makes -8. If you add +2 plus +6 minus 8, you get big old goose egg, 0. But that's a good thing because it's a neutral compound, and that means that we did our job right. Okay. Now, this table E is going to get real familiar to you soon. These are the selected polyatomic ions. Now, they're showing you essentially all the ions that are made out of the nonmetals in chemistry. The polyatomic ions are important. They're all nonmetallic ions. They're groups of atoms, polyatomic, polyatoms, and that are ions themselves. The ionic charge is always in the top corner, and it's not always written with a number. So the negative means -1. -2 obviously means -2, etc. Okay? So we're going to starting to be getting familiar with this stuff real quick. So, naming and writing chemical formulas, the very tip of the iceberg. Each element within a compound has its own charge. We call these charges oxidation numbers. On your reference, you have the most common oxidation numbers. And there's some rules for assigning these things, okay? Now, first of all, you have to make uncombined elements, not bonded to anything else, have an oxidation number of 0. Okay, this includes any formula that has only one chemical symbol in it. So single elements and diatomic elements. Some examples are like sodium solid, oxygen gas, and bromine gas. It's only one type of element. It's uncombined, meaning it's not technically a compound. The oxidation number must be 0. It's just a rule. Oxidation number for elements is 0, including the diatomic elements, Hofbrinkel, okay, or the diatomic 7H club. Now, in compounds, remember there's a neutral and have 2 or more different elements bonded together. The sum of those charges, those oxidation numbers, must add up to 0, kind of in the example that I did at the very beginning there. Big old goose egg we're looking for. So the ions within a compound have oxidation numbers equal to their oxidation number found on the periodic table or individual charges. For example, I'm going to use my periodic table that I got handy here to show you. Na has a selected oxidation state of +1. So that's really a Na +1 combined with Cl. Now, Cl's got some options, but we always pick the top corner as the most common option, Cl, with a -1. Okay, so a +1 and a -1. Well, these two combine to make 0. Big fat goose egg. That's the neutral compound the oxidation numbers are adding up to. Now, in magnesium nitrate, Mg3N2, you have to do a little bit more math. Magnesium's got a +2 most times, but it's +2 times 3, so that's +6. Okay, and nitrogen, we're going to take the most common one, which in this case is -3. So -3 times 2 is -6. Well, +6 and -6 is 0. Big fat goose egg. Yeah, we did it right. Woohoo! Now, an example of HNO3. You're like, oh gosh, there's 3. I can't do it. Ah! Well, not necessarily. It's easy to do. H is a +1 usually according to the rules. Oxygen is a -2 usually according to the rules. So that's a +1, a -6. So the nitrogen has to be +5. Now, you're going to know how to do this, that math that I put in there, by the end of this video. Okay? Nitrogen had to be a +5. These are the rules that I was just applying mentally, because I'm a chemist, I know this stuff. We always write the plus element, the positive element, metallic element first, and the negative, the non-metallic element, second in the compound formula. There's only a couple exceptions out there. Ammonia, NH3, is the exception. Ammonia. That stuff's underneath the sink for cleaning purposes. Hydrogen, that's a +1. Chlorine, it's a -1. So the hydrogen positive ion goes first, and the chlorine, the negative ion, goes second. Third rule, group 1 metals always have an oxidation number of +1. Okay? When in a compound, they're bonded to another species, some other element. Group 2 metals always have a +2 oxidation number. So you're looking at your periodic table, boom, there it is, selected oxidation state. Example, sodium, +1, and calcium is a +2. Alrighty. So that's that. Let's move on to our fourth rule here. Fluorine is always a -1 in compound. The other halogens, like bromine, chlorine, are also -1, as long as they're the most electronegative element in the compound. That's a little adjustment that I have never run into myself. So it's always really -1, and I've lived my life for most of my time with that. Never have to worry about chlorine or bromine being like -2. So these little guys, the halogens, are always going to be -1, which means that that hydrogen got to be a +1, that lithium's got to be a +1, and that sodium's got to be a +1, because they all have to, again, neutralize out. +1 and a -1. They always got to go to neutral compounds. That's how we do this job. Now, hydrogen is a +1 in compounds unless it's combined with another metal, and at the end of the formula, then it's a -1. So hydrogen's a little weird, and it's very rare that it comes up this way. But most of the time, hydrogen's +1, and it's playing the role of the metal, and the non-metal is the minus. But sometimes when hydrogen forms metal hydrides, it has to play the other rule, and it becomes a -1. Lithium, being from group 1, always has a +1, so therefore hydrogen in this case had to be a -1. So that's the one exception to the rule sometimes. Now, 6, oxygen's usually -2 in compounds. Again, I've never run into a situation where oxygen's not, unless you're talking about peroxides, and those are pretty rare. So hydrogen, like we said before, is always a +1. Oxygen, so +1 times 2 is +2. So therefore, oxygen in this case has to be a -2 to make a neutral compound. Now, carbon could be, we're not sure right now, but usually oxygen is -2. So if we do -2 times 2, that's a -4. So carbon, we can think something times 1 is +4, so that's got to be a +4 to make a +4 neutral compound. So we're just finding the oxidation states in these compounds. When combined with fluorine, it's more electronegativity, electronegative, oxygen is +2. I've never personally seen that. Oxygen fluoride, no, doesn't happen. So that's an exception to the rule that we don't really like to follow. But fluorine always being -1 times 2, that's a -2. Oxygen has to be a +2 in this scenario in order to balance and make a neutral compound. I haven't personally seen that except these notes. When a peroxide means O2. Oxygen is -1. A peroxide is a compound that has a formula of X2O2. Peroxide means there's 2 oxygens. Very rare again, but it's part of the system, so we got to keep it in there. Now, the sum of the oxidation numbers in a polyatomic ion must equal the charge on the ion on table E. So, for example, this is Cr2O7. Looking on my reference table, I believe that is chromate, is the name for that polyatomic ion. Cr2O7. Dichromate, see? Got to check my reference. I'm not perfect. Dichromate. So this is called dichromate. Dichromate. And it's ionic charge, according to reference table E, is a 2 negative. So in that case, the chromine and the oxygen combined have to add up to a total of -2. Now, oxygen is typically -2 by itself, so we can take a -2 times 7 equals -14, right? Now, chromium, I'm sorry, is something times 2 equals, we got to think about this, it's got to be equal to +12. Why? Because when we add the end, our final answer has to be the -2 that we see in the ion situation. So that something times 2 is +12. That's got to be a +6. So in that way, we're able to find out our oxidation states by kind of working backwards. Pretty challenging, but the concept is that number line math, really. Polyatomic ions have both ionic and covalent bonds. Okay? So, in the end, identify and list the polyatomic ions in the following compounds using table E. We'll do the first one together as an example. All I'm doing is playing the matching game. I'm looking at my table E from my reference table packet, and I am looking to see matches. So NH4, yep, there's one, NH4. And then the other one, PO4, yep, oh, there it is right there. So identify and list. So we have NH4, according to my list, it says it's ammonium. And then the next one, PO4, and there is phosphate. And there we have it. You named your first chemical compound from the formula. This is ammonium phosphate. Now, that sodium is not on table E. I don't see it anywhere. But I do see HCO3, which is hydrogen carbonate. Hydrogen carbonate. So, what your job is to do is to identify, play the matching game for your polyatomic ions. Oxidation number of oxygen is always going to be -2, except in peroxides when it can be -1. Therefore, the hydrogen for OH negative, for example, 1 polyatomics we're talking about here, must have a charge of +1. Okay, because the ion, polyatomic-wise, has an overall negative charge. Must add up to -1. That's the charge on the OH. For example, 2 PO4, 3 negative. Oxidation of number of oxygen is always going to be -2. So we have 4 of them times -2 equals -8 total. Oxidation number of phosphorus has got to be +5 because overall the charge has to be 3 negative. +5, -8 is a total of difference is -3, which is what we see in our oxidation state there. So I know this is complex, but we got plenty of practice to do in class. And so your job is to recognize polyatomic ions within compounds by using that table E, finding the formula and charges, assign oxidation numbers with compounds to using the periodic table as a reference and the neutral compound rules. And the relevant practice pack work is a lot of pages. We got 3 pages on that, and using table E to help us out there. So make sure that you ask me in class about how to do this stuff. Let's see, what should your Easter egg be here? You should do the Easter egg should be find out the selected oxidation states in the chemical compound CO2. Do the selected oxidation states for carbon and oxygen and CO2, and that is your Easter egg for this particular movie. Thank you all.